Hey Chem, Mrs. KJ here, going over 3.04, measuring acids and bases. The pH of a solution tells if it is acidic, basic, or a neutral solution. Calculating and understanding the pH of a solution is an important step toward understanding the properties of the solution. This lesson will look at pH as a measure of the acidity or alkalinity of a solution. And remember, alkalinity and basic are both talking about if something is a base. Goals for this lesson: describe pH and how it is used to indicate acids, bases, and neutral solutions. Relate the logarithmic nature of the pH scale to changes in hydrogen ion concentration. Interpret graphs that display information about acidic, basic, and neutral solutions. Given pH values, characterize solutions as acidic, basic, or neutral. Calculate pH when given the hydrogen ion concentration. pH indicates acidity with values of less than 0. pH indicates neutrality with a value of exactly 7. pH indicates alkalinity with values of greater than 7. And then, of course, you can download the student guide from slide 2. From the study guide, I added the first paragraph and the goals and our keywords and pronunciation. Alkaline, the chemical equivalent of basic, used as an adjective. pH is a scale from 0 to 14 that measures the acidity or alkalinity of a solution. A substance classified as an acid if it has a pH of less than 7. If 7, it is neutral. If more than 7, it's basic. Okay, this is where people get messed up for some reason. What about if I give you this value? If I say the pH is 7.05, what is it? Well, it's technically basic. Not very much, but it technically is because it's more than 7. So that's why we don't say that if it's 8 or higher, it's basic, because then that takes away 7.05, 7.5, 7.9. So that's why they use it as greater than or less than 7. Sometimes it is necessary to determine if a solution is acidic or base. Arrhenius, Bronson-Lowry, and Lewis are different definitions of acids and bases. These definitions are concerned with individual substances. Sometimes it is necessary to discuss whether a solution is acidic or alkaline. Remember, alkaline just means that it's a base. But before discussing solutions, we need to take a closer look at water. Pure water is neither acidic nor basic. We say that water is neutral. Water molecules can pass hydrogen ions, H+, back and forth while in motion. When a hydrogen molecule loses a hydrogen ion, it becomes a hydroxide ion, OH negative, and has a negative charge. Water molecules that gain a hydrogen ion will become a hydronium ion, H3O+, and carry a positive charge. So basically, water can go back and forth. Water contains both H+ and OH negative ions in small concentrations at all times. So that's why it's partially acidic, partially basic, and really overall it just ends up equaling out at equilibrium and being neutral. Water molecules produce ions in a process called self-ionization. The self-ionization of water is written as below. H2O yields H+ plus OH minus. So basically you just break the water down. It becomes a proton or a hydrogen ion, and it becomes a hydroxide ion. Arrhenius talked about H+ in his definition of acids. It is just as valid to talk in terms of the presence of hydronium ions. In this case, the formula is H2O plus H2O. So we have two water molecules put together, and they yield H3O plus, or a hydronium ion, plus hydroxide. This accounts for the creation of the hydronium ion, H3O+. This process of self-ionization occurs naturally. At 25 degrees Celsius, the concentration of H+ ions and hydroxide ions are equal. The concentration of each is 1 times 10 to the negative 7th molar. Remember, this stands for molar, or moles per liter. Water is a neutral solution. Okay, and we'll get back to why this is important. We'll come back to that. All right, so we have a neutral solution. If we look at the particle view, we can see that although this is water, we have that it can break up into hydrogen ions and hydroxide ions. And 1, 2, 3, 4, 5, 6, 7, 8. They should be equal. 1, 2, 3, 4, 5, 6, 7, 8. Yes, they are equal. The concentration of hydrogen ions and hydroxide ions are equal. In 1 liter of water, only 0.0000001 moles will be either hydronium or hydroxide ions. Okay, so really you have hydronium ions instead of the H pluses floating around because the 2 water molecules are going to go together, and this still has the positive 1 charge because it has the extra hydrogen. So in a way, we're saying that instead of having the H plus, you have the H3O plus, and that's the acidic part. So in a way, I don't want to say they're equal, but in this case, they stand for the same thing. They stand for it being acidic. Okay, so we have equal numbers of each, but most of what we have in this container is H2O, and they didn't show us that. Okay, so most of this is H2O, but this small percent of moles is going to be either the hydronium, the H3O plus, or the hydroxide OH negative ion. The concentration of hydroxide ions when multiplied by the concentration of hydrogen ions is equal to a constant. If the H plus or H3O plus, remember we're using it interchangeably when we're talking about which is the acid, if that concentration in solution increases, then the OH minus concentration must decrease. The opposite is also true. The equilibrium will shift when ions are added to a solution. Okay, so water had equal numbers of hydronium and hydroxide. If you have a solution and it has more hydronium ions, then you have to have less hydroxide. If you have more hydroxide, what has to be true about the hydronium? It has to be less, because it always has to balance. So if one goes up, the other one goes down. The equilibrium will shift when ions are added to a solution. This leads to an important point. In an aqueous solution, or when you have something dissolved in water, the product of the concentration of hydrogen ions and the concentration of hydroxide ions is always equal to 1.0 times 10 to the negative 14th molar. Okay, now 14, where did that number come from? Remember I said your pH scale only goes up to 14. So when you add in the concentration of hydrogen ions plus the concentration of hydroxide ions, you're always going to get this as a total, which is why our scale is out of 14. This product may be expressed mathematically as concentration. So remember these brackets right here mean concentration. So the concentration of hydrogen ions times the concentration of hydroxide ions equals 1 times 10 to the negative 14th molar, or moles per liter. So we have our neutral solution, the concentration, of course, of hydrogen ions times hydroxide ions equals 1 times 10 to the negative 14th molar. In pure water, both the concentration of hydrogen ions and the concentration of hydroxide ions are 1 times 10 to the negative 7th. Okay, oh, hey, what's the pH of water? 7. Yeah, so that's where we get our pH values from. It's actually based on the concentration, specifically the molar or moles per liter concentration. And then if you multiply it together, so the fact that they're equal, they're both times 10 to the negative 7th. When you multiply that together, you get times 10 to the negative 14th. Now, if you're thinking to yourself, 7 times 7 is 49. Yeah, but remember, in math class, when you multiply exponents, you actually have to add them. Remember that from math class? So since it's 10 to the negative 7th times 10 to the negative 7th, you really add the exponents, and that's how we get 10 to the negative 14th. Okay, so what I added to our notes from those last couple slides. First of all, let's talk about pure water. It's neutral. What that really means is it has equal amounts of H plus and OH minus ions. So equal amounts of hydrogen ions and hydroxide ions. Specifically, 1.0 times 10 to the negative 7th molar. of each. Okay, and remember when you write molar, it has to be what? Italicized. Water molecules produce ions in a process called self-ionization. The self-ionization of water is written as below. So a water molecule turns into a hydrogen ion plus a hydroxide ion. And when two water molecules come together, they make a hydronium ion plus a hydroxide ion. And then to remind us, this H3O plus is a hydronium ion, which is obviously different than just a hydrogen ion, yet both are the indication of an acidic solution. Okay, so in a way we use them interchangeably. When we see hydronium or a hydrogen ion, you should think acid. When you see hydroxide, you should think base. All right, so let's talk a little bit about pH. I know it hasn't really started talking about pH, but in a way they did. So I put it under the heading of pH. If the hydrogen ion or hydronium ion concentration in a solution increases, then the hydroxide ion concentration must decrease. So when one goes up, the other one goes down. The opposite is also true. In an aqueous solution, the product of the concentration of hydrogen ions and the concentration of hydroxide ions is always equal to 1 times 10 to the negative 14th molar. And of course, you can express this mathematically. And very important that you remember, whenever you see those brackets, okay, so the brackets mean concentration of. So make sure you're reading that correctly. Some solutions are neutral, but obviously not all. Certain substances, when dissolved in water, will release a hydrogen ion. In this case, the concentration of hydrogen ions in the aqueous solution will be greater than the concentration of hydroxide ions that exist as a result of self-ionization reactions. The balance has shifted in this solution. The concentration of hydrogen ions is then greater than 1 times 10 to the negative 7th molar. The solution is acidic. So if you have more hydrogen ions, it has a concentration more than to the negative 7th, because remember, negative 7 tells us it's neutral, a pH of 7, and that tells you the solution is an acid. Other substances may release hydroxide ions when they dissolve in water. This shifts the balance the other way. There will be more hydroxide ions than hydrogen ions. The concentration of hydrogen ions is now less than 1 times 10 to the negative 7th molar. The solution is now a basic solution. You may also see this referred to as an alkaline solution. So remember, alkaline is basically a synonym for the word basic, which means a base, and it's used as an adjective. All right, so let's look at ion concentrations. Okay, so here we have an alkaline solution. What do we have more of? We have more of the OH molecules, or the hydroxide ions. When you multiply the concentration of the hydrogen ions times the concentration of the hydroxide ions, you're still going to get 1 times 10 to the negative 14th molar. Remember, our pH scale is out of 14, so that's always our total. But the concentration of hydrogen ions is less than 1 times 10 to the negative 7th molar. Okay, remember, they both started out as times 10 to the negative 7th. If you have more hydroxide, obviously the hydrogen ions is going to have to be less than what you started with. When you're neutral, you have exactly 1 times 10 to the negative 7th of both the hydroxide and hydrogen ions. And of course, when you multiply them together, you get 1 times 10 to the negative 14th molar. What about when we have an acidic solution? Still, when you multiply them together, what do you get? 1 times 10 to the negative 14th molar. And this time, though, the hydrogen ion concentration is greater than 1 times 10 to the negative 7th molar. So you have more of the hydrogen ions over here, obviously in the picture. In this one, you have more of the hydroxide ions, but both times when you multiply the concentrations together, you always get 1 times 10 to the negative 14th. So to our notes, I added, if a substance releases hydrogen ions in water, there is a higher concentration of hydrogen ions than hydroxide ions, and the solution is acidic. The concentration of hydrogen ions is then greater than 1 times 10 to the negative 7th molar. Conversely, if hydroxide ions are released